just as soon as I can start this thing up. There we go. Got the message deleted. And Discord. Here we go with the analog to digital conversion. Now, you can look this guy up, but I'm going to go back a little bit. And during my quests to make sure that I was leading in the correct path of Bravo 8 Zulu Sierra for the scenario, I came across the CDI. If you were to look up condition diphase, you're going to come up with Manchester diphase. But upon my search of the B8ZS, I found something that resembles CDI. They call it Manchester differential. So why we got it CDI, I have no idea. The only thing I can think of is the way the manufacturer put it out. But let me ask you there, let's choose Liverpool. What are the 3 self-clocking modes or 3 self-clocking signal formats that we went over today? Silence is deafening.
Sheesh.
No idea? You can say I don't know.
I'm not sure, sir.
Okay. Shinsky?
Oh, wasn't one like RZ bipolar?
No.
I'm not sure,
You're
sir.
close.
Is it the RZ polar?
There's one of them. O'Brien, can you name one of them?
Bipolar zero suppression is the other one. I'm not sure about the third.
Yep. Those are 2. RZ polar, RZ bipolar with zero suppression. The Liverpool. Notice that we added that zero suppression on there. Okay. Let's ask Rada what the last one is.
CDI, sir.
Bingo! So those are the 3. Yes. So now we're going to change gears and go into something called analog to digital conversion. You guys have already played with this. You're going, no, we haven't. Yeah, you have. Block 2, PRIC 150, uses PCM, analog to digital, to modulate the signal. Okay, so how does it do it? Well, we're getting ready to go over it. Dr. Nyquist, hence the Nyquist theorem, said that when we look at converting digital or analog information to digital information, we need to find out where the average voice frequency is. And he figured out that between 300 to 3K was a pretty decent area. But if you take a look at some of these radios, they'll actually go up to 34, and I've seen one in my whole career that went to 36. But what he said is anything over 4K causes this thing called sideband foldover, which means it's distortion. And he didn't want distortion when he was doing this. So he said, okay, let's do this. Let's round it up and say, hey, from 0 to 4K, we're going to do this theorem. It's called 2 times the highest audio frequency will give us the sample rate. Well, 2 times 4K gives us 8K, or 8,000 samples per second. And that's mainly for our voice channels. And if you take a look and you go back and you do your research with Block 6 and get into the holy crap with the signal formats and everything else, you will notice that the 8,000 times per second relates to the 64K when we are talking about a voice channel. Yes, everything is related here. So when he looked at this, he said, we're going to use something called PCM, Pulse Code Modulation. There are 3 steps to it. The first step is sampling, the second step is quantizing, and the third one is encoding. So when we do this, we use the term sampling. Remember, we talked about sampling, saying, hey, this is how we're going to do it. Here's the analog signal. We're going to do this in sequence. So 1 second, how much of that analog signal we're going to sample it 8,000 times in sequential order, and each one of those sequences will be equally spaced between each other. That's horizontally. Now we're going to go ahead and look at the pulses and measure those pulses and take a sample at that particular time period. It's called pulse amplitude modulated pulses. So PAM, like the spray, not Peter Pan. No? Okay. You're right, Senior Airman Ward. This is a tough crowd. Next up, we got PCM Step 2 called quantizing. What are we going to do with it? Well, we're going to take... Good one, right? Well, someone's enthusiastic. We're going to take this signal, all these pulses, and we're going to put it on a table. And it's going to resemble the signal in what it was in the analog form. And that's quantizing. So what I did here is I took a piece of graph paper to give you an idea how they are, number one, horizontally spread apart. Number two is we're going to put it on a table that has 127 lines from the 0 line, 127 lines to the top, positive side. And then we're going to look at the bottom where we're going to take, 127 lines to the bottom, all the way up to 127 from 1 to negative 127. Every one of these are equally spaced. Well, when you do this, we call this table a uniform quantizing method. So there you go. It's going to contain 254 steps. That's basically 127 one way and 127 the other way. That's 254. Well, what's the total of an 8-bit word? Anybody remember? And everybody's going, huh?
256, sir.
256, huh? Really?
255?
I like the 255 because when you add all these up, this first 7 bits is 127. 127 plus 128 gives us 255. Seriously, 255. Ah, gosh, I can't overstep in here. So, with uniform quantizing, there's a problem. 254. I can't believe I wrote that down there. Hang on just a minute. Yeah, it is 254 steps. Okay. Uniform quantizing is where we are going to get rounding. They call it a quantization error. That's the rounding bit. What is it going to sound like? Well, if there's a bunch of them, it's going to sound pretty distorted. So how do you combat uniform quantizing? Well, what they did is they developed this thing. Again, it's the same space between the 0 to the 127 and 0 to the negative 127. It's the same space. However, what they did is they started scrunching most of the lines together to where, believe it or not, the normal voice is. When they say normal, they built it for the masses. They didn't build it for each individual. So with this in mind, by scrunching those lines together where the normal voice is, and then when it starts to where most of us either exceed, do not exceed it, that's where the lines started spreading apart. This compensates for most quantization errors. Now, quantization errors are still going to happen in there, But the problem that you have is if you got somebody with a very high-pitched voice or a very low-pitched voice, more than likely you're going to get down out into that area where it will have to be quantized error in order to compensate. So quantization errors are still going to happen, but just not as many as it would if it was uniform quantizing. So there's your two steps. You got first step is sampling. So we're going to take all the samples and then we're going to quantize it by putting it on a table. We're going to use the non-uniform to help us with the quantization errors. Quantization errors being the rounding. The next thing is encoding.
So,
Go ahead.
so quantize is a like a unit?
Yes. What they're doing is they're putting a number to that pulse. Anywhere from 0 to positive 127 and 0 to a negative 127.
So is that like when you hear it's like the voice, how it goes up and down and all those waves? Is that what I was talking about? Is that the quantizing there?
Okay. That's the sampling. It's looking at that wave. We're going to sample it in equal segments, and then we're going to put a number to it. That's what the quantization is. We're putting a number to it. Anywhere from 0 to 127 on the positive side and 0 to 127 on the negative side. So here is, go ahead.
What would make it go negative?
What would make it go negative? A
Like,
low
is
pitch.
the lower it is, the more negative it goes, or the higher?
Okay,
more
think of
positive,
it,
or-
yeah. Lower the voices would be into the negative, and the higher would be in the positive. That makes sense? I'm going to show you, you just now toggled a piece of my memory and go, oh, I got a, it's an Air Force application, but I'm going to try to show you what it looks like when it goes from the analog waveform to the quantization to the encoding. All right, so maybe that might help you with this particular waveform. And I'll show you here after we get through with this particular 1 Bravo. Okay? Good to go?
Yes, sir.
Okay. So the next step is now we got these numbers. How do we get it to the 8-bit word? So when we look at this, we're using 1 all the way up to 64 for our 7 bits. The 8-bit tells us where it is either above the 0 or below the 0. Let's take a look at this. Here's a chart. You can see where all the positive numbers, and this is going from right to left. You can see that we have 0, 1. Well, that would give us 2. And the 8-bit tells us it's a 0. Now, that's kind of bad, but I always thought that, well, gee, if it's a positive, don't you think it would have been a logic 1? Well, for some reason, the engineers thought this through and said, no, positive numbers will be 0, the negative numbers will be 1s. Don't ask me. I was not in there when the engineers developed this. So for number 4, it's 0, 0, 1, and then all zeros to give us the 4. That's above. And then we're going to go down lower to where we see the last number being a negative 2. Well, it's 0, 1 because it goes 1, 2, 4, and so forth and so on. Well, the negative number, that last number, is a 1. So that tells us we're going to be below the 0 line. So there's your 3 steps of pulse code modulation. You got sampling, quantizing, and encoding. So what corrects for quantization errors? Anybody?
Non-uniform quantizing?
Non-uniform quantizing. Yes, good job. So now we're looking at a couple of terms here, and I want you to pay close attention to this. frame period, the time it takes for one frame to occur. Well, you've seen back in the other segments there about what a frame looks like. It is taking all of those channels and going, okay, at 8,000, frame periods, which is 8,000 times a second, I'm going to be looking at, let's just say, 24 channels, because 24 channels supposedly is the standard when we are looking at this. So it's 24 channels in 8,000 frames per second. In that frame period, we're trying to figure out how long it's going to take to measure that, to look at all 24 channels for that sample rate to occur. So we're going to take 1 over 8,000, and we're going to get 0.000125 seconds, or in our case, just showing you 125 microseconds. That is a frame period. That's the frame time it took for one frame to occur from channels 1 through 24. The next term that we come across is pulse modulated sample period. The time it takes to sample one channel in any given frame. So what does that mean? Well, remember I told you the frame period's this long. It's 125 microseconds to look through all 24 channels. All 24. Now, with pulse modulated sample period, we're looking at one channel. How long did it take us to sample that one channel? Well, we're going to take the frame period that we got, which is 125 microseconds, and we're going to divide it into, we're going to take 24 and divide it into it. We end up with 0.0000528 seconds, or 5.28 seconds. In other words, frame period was 125 microseconds. The time it took to sample one of them was 5.28 microseconds. That's, for channel 1, for channel 2, for channel 3, for channel 4. Now, if I had the old FCC 100, it would be different. Instead of 24, it would be 16. So it does depend on the number of input channels and how you divide the frame period. We've gone over general multiplexing terms, data relationships, types of multiplexing, modes of TDM, demultiplexing, signal formats, and analog to digital conversion. Any questions?
Not this time, sir.
Yeah, everybody's going, man, this is overwhelming. I know. Been in your
Yes, sir.
shoes. Been in your shoes. About 30 years ago. Okay, so let's look at one chart. Identify basic facts about network band management equipment. And again, I can't emphasize this enough. You need to get at least 28 or more to pass. That is correct answers. You can only miss 12 out of that 40 question test. Here's the Air Force application. You may have to figure out bandwidth. In the old FCC 100, you had to figure out bandwidth along with programming the cards. Next up, we got bandwidth allocations, network infrastructure, transmission media, carrier system concepts, and hierarchy. Take a look at each one of them. The easiest way to go through this one is there are 4 conventional, demand assigned, dynamic, time of day restrictions, bandwidth allocations. There's 4 of them. So those are the 4. Just going to explain them quickly. Conventional means that you're going to have a fixed amount for each user. The problem is if you don't use it, you lose it. There you go. You can see we have 4 channels. Each one of them is 64K. Grand total 256. So your bandwidth is going to be 256K. Problem is if you're not using it, wasted bandwidth. Next up, we have the demand assigned. This is when you get assigned X amount, and it is very likely if not enough people on, you can exceed that. For example, AT&T, I think it's 25 up and 5 down for me, which means that, oh, gee, that's the internet. Well, if everybody on my street is not using their segment and I want to, let's say, play World of Warships on one screen and World of Tanks on the other screen, and I exceed the bandwidth, but no one's online, hey, there you go. There you go. I can use it. Not that that'll ever happen because I'm not a very good multitasker. I can barely get my tank to go forward and backwards and left and right with the mouse shooting. Okay, demand assigned, here you go. You got one user that's assigned 64K, the other is 9.6, and then the other one's 56. They can have that. That is their maximum. If it's available, they can use what's available. You still have 256K out. But the moment you exceed 256K, here comes AT&T and they're going to throttle you. Oops. Or if you use too much of it, yeah, that's going to happen. Then you have demand assigned. This one means that you can exceed, but it works like the trunking system. You guys remember Block 5 and the trunking system? They give you X amount of frequencies, even though that everybody could exceed it at any given second. But the chances of it doing that, where everybody gets on at the same time, is pretty unusual. Again, here you can see that our total bandwidth, you can see we got 264s and 128Ks for each one of them, ends up grand total of 384, but it exceeds the bandwidth. The question is, am I going to use it all? Probably not. Next up, we have time of day restriction. I like to use the old that movie, Lone Survivor, where they were up in the mountains and they had to call back to base once a day between a certain time. Well, gee, there's your time of day restriction. Why? They had priority. In other words, you will call the base between 7 and 8 o'clock. If you miss that time, you can't get on. So if they were in the world of hurt like they did that last time, they had to use a sat phone. That one didn't have a priority on it. Also, if you watch the movie, you can tell it's like, why in the world would they try to do SATCOM back to base in the tree line? Did not make any sense. Oh, gee, they didn't have a radio person with them. Sarcastic works, huh? Next up, we have network infrastructure. Network versus intranet, which is between, what you would have in the house. Network is when you're connected to the server and you're talking, for example, every once in a while I'll get on the European server and play a couple games and get my butt beat, but I learn as I'm doing it. I go to the South American server and they have bots down there. And sometimes the bots are good, and most of the time the bots are bad. So if you needed to get your experience up on a tank, there you go. Go to the South American server. But it just goes to show you, I'm talking through a whole network here. And the ping rate on the South American server is between 200 and 500 on a consistent basis. But you go to the European server, it's between 200 and 400. So you got me. Now, we do have something called submarine cables that connect the Europe to the United States and South America and so forth and so on. You can look it up. Take a look at the submarine cable system. It's huge. That's how we get all the networks tied together from overseas. So next up, we have something called the Electronic Industry Agency. These people are the ones that made interoperability a mainstay for the industry. Without them, we would still be doing Apple computers with Apple printers with Apple this, instead of being able to talk to an Android and a PC and so forth and so on. So that's the reason why these standards came into play, is they wanted everybody to follow the standards, and then the companies wouldn't be faced with having a monopoly on something and then they would have to be broken up. So this was the easy way around to keep these companies from becoming a monopoly. So we had the EIA 232 Charlie and the 530. So let's look at the 232 Charlie. And if anybody has ever had the old 56K modem, you know what I'm talking about. So look it up on YouTube and you'll hear that sound. Anybody ever had the 56K modem?
Yes, sir.
So you know what I'm talking about. That's wild. Of course. I must have an older generation in this one because I had last class, they went, What's a 56K modem? Kind of unusual. Then again, you're older for sure. Yeah, that was back in the late 90s is when I finally got one. I want to say about 98. And it was slow as Christmas. Well, actually, yeah, 99 for you? Okay. I can tell you this much. My mom lives in the middle of the Daniel Boone National Forest in Kentucky, and she's got fiber. I'm jealous. But anyway, what does it mean? It means 56K, 50 feet, up to 500 to 5,000, then you're going to be, geez, slow as Christmas. Sounds like the AFNet computers. I thought a Commodore 64 was slow. Anyway, EIA transmissions lines. So why do we come into play? Well, we have two different types when we're sending data across right now. Mine is on a twisted pair. Now, the interesting thing about a balanced line is you have the twisted pair, and one is the original signal, and the other one has been flopped about 180 degrees out of phase with it. The idea is when I do that, I know that I'm going to get noise down the line, so when it gets to the distant end, it puts it back together, and believe it or not, takes the noise out. It cancels the noise. It is the precursor to your noiseless or noise canceling headphones, because your noise canceling headphones takes anything from the outside, routes it to the inside. So if there's any of that that gets into your system there, it'll cancel it out. That's how they work it. Amazing, isn't it, how technology has worked. Again, this is your twisted pair, your telephone lines. The next one is an unbalanced. This is your coax cable. All your data goes to and from on a single conductor. The shield, which is the outside of your RG whatever, is grounded. Now, the idea behind that is with the shield and it's grounded, it's going to prevent noise from getting on the line. At least that's the idea. If you have a poor ground, you're going to have some issues. Next up, we have something called a DB connector. Now, if you have the netbooks that was issued to you, anybody in here have a netbook that was issued to you? In other words, you didn't have a computer and they hand receipted you a computer. Pretty darn small. No one in here has a netbook. Anybody want?
I don't think so, sir.
You have a netbook?
No, I don't, sir. I said I don't think anybody has one,
Okay.
sir.
Well, the netbooks that were issued out have a D connector. It is a 25-pin D connector, and you can connect it to an old-style monitor if you wanted to. Nowadays, what is it? It's an HDMI, it's a display port, you name it. So it's changed, but we still have these out there, and you're going to be in room 116 tomorrow, and you're going to be using, I think it's a 50-pin D connector that you're going to be inserting into the back of the NSM case when you're putting the HST 3000 on it. So you will be coming across those. Now, we used to have the old 9-pin printers, which had 9-pin D connectors. And of course, we still have the 25s, the 50s, and I even think there's 100 out there. Now, with this EIA electrical characteristics, all they're trying to do explain to you that sometimes there is this thing called negative logic, where a plus voltage equals a 0 and a negative voltage is a 1. I've used negative logic. I shouldn't say I worked on a piece of equipment called an OJ314 that used negative logic. And sometimes it gets a little confusing when you're trying to figure out if it should be a high or a low depending on the we troubleshoot down to the component back then. But it was difficult trying to remember that. Next up, we look at the EIA 530. This is the improvement upon the 232 Charlie. This one is what we are using today, and it normally is without the use of the modem. Most of the time, like for example AT&T, we send it out, we send it through a modem / router to the central office. In my case is probably less than half a mile from my house. So I mean, it gets pretty good. On occasion I'll get some pretty good speeds late at night. Next up, DTE and DCE equipment. You're going to see this when we get to the NSM / the HST 3000, better known as a BERTS, built-in test equipment. Excuse me, bit error rate test. Excuse me, that was bad. Bit error rate test. All right, so we have the DTE and DCE. The DTE is a computer. It is the beginning and where you're going to send out the information. And at the distant end, you're probably going to have another computer on the distant end, and that's the destination. So versus the source or the destination. Next one, we got TCE, which is the communication device. How did I get my information from the computer to the distant end? Well, we had to modulate it. And then when it gets to the distant end, it's going to demodulate it and give it to the computer. That is the communication device between the two. There are 4 different types of transmission media. We got a twisted pair, coax, fiber optic, and wireless. So we can go through these. Twisted pair, you are familiar with Cat5, or in my neck of the woods, excuse me, you're going to be dealing with telephone wire, which is a 2-pair, grand total of 4 total wires. That's how it gets in on my house. Twisted pair, baseband only. Wow. It is a balanced line as opposed to a coax cable, which is an unbalanced line. Excuse me. And using Sparklight down here, it's coax cable, but most of it is now fiber. We have fiber optic cable, which is, a light, which is a form of RF. It's in the terahertz area. Did you guys know that you can hear RF? No? Maybe?
No, sure.
Okay, the RF spectrum by the international agency says the start of the RF spectrum starts at 3 kHz. You can hear up to, in my hearing, it kind of tapers off around 17 because I lost the upper end due to, oh, wait just a minute, electronics. Especially with the OJ314, that had a inverter on it that would squeal so high. Anyway, yes, if you can hear anywhere between 3K to 20K, that's somewhere in that vicinity, that's RF. That is RF. And then you can see RF, which is light, and that's in the terahertz. So you got hertz, khertz, and then terahertz. So those are 2 visuals, excuse me. One is audible and the other one is a visual. So those are 2 styles of RF that you can actually, with your senses, look at. Fiber optic is part of that. Wireless, that's over the air. How do we even get with it nowadays? Your phones, your Wi-Fi service, your hotspots, so forth and so on. Next up, we have something called a DSU. This is a digital service unit. You're going to see it in, if you were at, let's just say AT&T. I use that because that's what I have. With AT&T, if you call them out and say, hey, I got a problem with my internet, they're going to ping the DSU. The DSU is going to check your end to see if there is a problem. It's going to use something called AMI, alternate mark inversion. Where have you heard that? Oh, gee, it looks like it's RZ bipolar. It is on the customer side of the network. Customer side. User, customer. It does loopbacks to check and see if your equipment's working. And it always kills them that when you get someone who understands the network to a certain degree, and you say, well, I've checked this, it's on y'all's end. What? Yeah. If you go and you hit this, you'll find out that my loopback works just fine. What you won't find out is when you're trying to hit it, it doesn't get anywhere because of your CSU can't see the failure. And they just kind of, really? So DSU is the customer side or user side, alternate mark inversion, but with the channel service unit, do not confuse the letter C for customer. I see that a lot out there. C stands for channel. Channel being the network side, and it uses bipolar with zero suppression. And Rita, this is where I found the crazy thing about the police one's density. It throws a bit violation, even though it's an 8-string 0, it will throw a bit violation at the fourth one, give you a 1, a 0, a 1, and another bit violation. I'm like, what the heck did I just see? And it talks about policing ones, zeros. It throws that in there to let it know that, hey, these are ones. This is on purpose to sync everything back up. All right, so the DSU and CSU are normally in one box. But here on this diagram shows you how we got them separated out. The DSU is on the user side or customer side. The CSU is on the network side. Please do not get those confused. Here is the hierarchy. And this all relates to your voice channels and how they develop them. So we look at 24 channels. It would give us 1.55 megabits per second. The whole idea is that gives us one multiplexer. That's a T1 line. We look at a T2 line, that's, I think it's 4 T1 multiplexers going into another multiplexer. And that gives us a T2 line. Well, when we get to a DS3 or a T3 line, that's where we see, I think it's 7, I think, multiplexers that are T2 multiplexers going into one multiplexer to give us the 44.736 megabits per second. Remember now, you need more bandwidth, you're going to have to add another multiplexer. This one is about the best diagram that I can come up with to give you an idea how the T1, the T2, the T3 lines work. From my understanding, when I did my research, when you hit T4 lines, they start developing something called superscripts, which are errors because they're going so fast and the bandwidth's so huge. So it creates problems. So I'm pretty sure that was taken, several years ago. I have not done any more research on it. So just to give you an idea how crazy things have gone, and the technology has probably exceeded this by now. Because I know that they've got, isn't it a Google Fiber? They've got it at 1 terabyte now. Can anybody remember? Or is it 1 gig?
I think it's 1 gig, sir.
Okay. I know that they were doing, the reason why they're trying to increase everything is because the 4K TVs, there's no guidance on how the over the air and streaming can get to 4K. I don't think of any that does 4K. Does anybody know? Streaming wise, nobody does 4K streaming? No?
Not that I know of, sir.
Okay.
I don't think so as of yet. I could be wrong though.
Yeah. It's another thing that I go look up. I love to do some research on occasion. This feels like one of those days again. I do know that the reason why you have Korea and Japan, you compare those two with ours. Ours is like 26 compared to those two. Those are like number 1 and number 2. Well, they're working on a 10K TV, and man, that'd be freaking crazy, as far as details are concerned. So there you go. That's the reason why we're struggling to keep up, is because of the technology. We got so much here that by the time we build the infrastructure, it's already over with. They're talking about the 5G catching up. It's like, oh, okay, well, whenever. I'd still like to get my, ping rate down, i.e. get fiber in. Well, anyway, sorry I digressed there. We've gone over bandwidth allocation, network infrastructure, transmission media, carrier system concepts, and hierarchy. Can anybody name the 4 bandwidth allocations that we talked about? Wow.
Conventional, demand assigned,
Okay.
dynamic,
Okay.
time of day restricted.
Outstanding. Wow, you and O'Brien are fighting it out, ain't you?
That's why they're the hundreds.
Yeah. You're on the JOB. Okay, good job, Rita. All right, so let's go to the next one. 1 Delta. Identify basic facts about principles, capabilities, limitation of multiplexing equipment. Let's take a look at what we're going to be looking at. Oh, the NSM50, which you're going to be working on starting tomorrow afternoon. We're going to look at the purpose, the functional description, operational characteristics, NSM configuration. This is what it's going to multiplex. This is how many input ports and so forth and so on. Why am I going through this so quick? I'll tell you in a second. Okay. You got uplink, downlink on the back of the NSM. This is what you're going to see. On the NRZ ports is what you're going to be playing with. These are 50-pin ports, if my memory serves me. You're going to be using the HST3000 with it. Just remember, there's 4 different sections to the NSN. They're the 6 CDI ports, 6 T1E1 ports, 12 NRZ ports, and 2 HISI ports. It's high-speed serial interface ports. We'll go over the extract here in just a minute, but I want to get through the HST, which is 2 alpha. We're going to identify basic facts about the capabilities and limitations of the bit error rate test set, better known as a BERTS. In our case, we're going to be using the HST3000. You're going to use it starting tomorrow. We're going to look at what it does for the basic, and then we're going to look at the HST3000. So this is what it does. Performs tests and loopbacks on a system to adequately analyze signal quality as it travels across the network. So you can use it inline or alongside. You can use it as a DTE or DCE. In our case, we're looking at the HST3000. If you wanted to purchase one of these right now, you can go to eBay and purchase one for about $3,000. They still have them out there, even though the manufacturer's already gone on to a probably about 3 different new models now, but it still works. If it ain't broke, don't be the Tim Allen and say, I can fix it. I can give it more power. You don't need it, really. There are 3 test modes that we go over with the HST. You got DT emulation. In other words, it acts like a computer. You got DC emulation, where it acts like a modem. And then you have monitor to check and see how many bits are going to and from, and if there is an error. That's what it's used for. Bit error rate test set. That's the HST 3000. So there you have it. So with that in mind, let's pull up the C's and D's for the NSM, and I'm going to quote this. This is a 31 Romeo 2-2 Tango Sierra Charlie 179-2 extract NSM 50 operator's manual. That's the PDF file that I'm going to be looking at. Hopefully it'll fit in here. Oh, good, it does. All right, so this is the NSM 50, and you can either follow along or you can watch me go through this. I think the first page we look at is here we go. Is the introduction. This is telling you what it is, and for most part, what possibly it could do. Now we're into the nitty-gritty. So this is a general functional description. Notice I got that whole paragraph on 1.3 underneath the note highlighted. What it's telling you is this is what it does as multiplexing, and this is what it does as demultiplexing. And I'm going to caution you. Normally, they will tell you everything it does in multiplexing and just lightly touch on demultiplexing. Just remember this. If it multiplexes, it's got to do it in demultiplexing. So in other words, if I am encrypting my output, then I have to decrypt my return or demultiplex it. So decrypt, encrypt. Multiplex your encryption. Demultiplex, you got to decrypt it. It may not say it decrypts it, but you should assume that it's going to do it, because it doesn't make any sense to encrypt it to send it out and get it back and it's not encrypted. Doesn't make any sense. So this gives you some information. I just wanted to point 1.3.1.4 for control computer interface. You'll see it says RS-232 and 422 DTE signals. Just to give you an idea that we're just not so, spouting information to be spouting it. No, we're going to use it. Charlie. On that 1.3.1.4 computer interface, Charlie, it says when using the GUI, that's graphical user interface. In other words, you're going to be using a computer with the equipment. Now, if you take a look above me, besides the 3389, you will see 2 pieces of equipment. One is a 3-case entity. This is the TSC 179. On the far left is where the NSM 50 is, and on top of it is a computer. Above that case is something called the iDirect. I highly encourage you, when you get into the room 116, take a look off to the left. That's the iDirect. And we'll be talking about that when you guys have already completed your NSM PCs. or practices and PCs. So just letting you know, please take a look at it. You can ask the instructor, hey, is that the iDirect? And they should go, yeah, that's the iDirect. And where are you going to use it? You're going to use it in Block 9. It is a satellite modem. So with this, going back over the more information on the NSM, we're going to look at the ports that I just highlighted earlier. The first one is an NRZ port. Where have you heard NRZ at? I wonder. Non-return to zero. It doesn't say if it's polar or if it's neutral. I don't know what it is, but it doesn't say it. I'm sure if you pulled out the O-scope and hooked it up, you could probably see it. Now, two things you need to understand here. It says on number 1, it says legacy, and number 2, it says enhanced. Legacy meaning the older equipment, like me. Enhanced being the newer equipment, like you. Okay? You guys are the new kids on the block. I'm the old fart. So, legacy, old fart. Enhanced, new fart. Okay? So there you have it as far as the differences between legacy and enhanced. Now, I do want to caution you, they will ask on occasion, hey, what's the max data rate for legacy mode? Anybody? Max data rate for legacy mode.
$1152 kilobytes.
Exactly. What you do when it says the max data rate, you look for, is it the max data rate for all the ports in some instances, or is it the max data rate for, in my case, I asked for the legacy, so that's 1152K. If I ask for the max data rate for the NRZ group port, then you're going to have to look at the enhanced, because the enhanced is a newer equipment, because it's going to go faster. And you're going to see, oh, gee, it's 8448 kilobits per second. Let's look at Charlie, where it's a T1E1 ports. Must be bipolar. And here's where that little saying of the B8ZS is. And if I'm not mistaken, this one is the one where they throw the 0 at the 9th one. Of course, then again, interpretation. And then with the E1, it says AMI HDB3. This one definitely throws it at the 4th one. I verified that today. I found it in 2 different spots. But you can see it says AMI, alternate mark inversion, which is telling you, hey, this is bipolar. And then you look at that little number there, HDB3, which is 0 suppression. There you go. There you go. Now that one, you can see the E1 does better than the T1. So it's got 2048 kilobits per second. The other one has 1544. So the max data rate for the T1E1 would be the 2048. Then you have a group modem, which is CDI, conditioned diphase, or if you looked it up online, it's probably Manchester differential. And if you ask for the max data rate again, you would go to the enhanced mode and you would see that the max number on there is 4608K. And then you have the HSI, the high-speed serial interface. Now I want to point to you, it says EIA 530 or EIA 613. It has everything to do with what's on the back of the case. Will determine whether it's EIA 530 or if it's the EIA 613. In our case, would say, well, gee, the max data rate on this is 52 meg, or 52,000 kilobits per second. So if I had to ask you guys, what is the max data rate of the NSM50? You're going to look up the max data rate of all these ports, and you should say, oh, gee, the highest one I see is from the HSI, which is 52 megabits per second. It's that easy. All right, so this is the peripheral equipment. I'm just pointing it out. You got the computer. It's a tough book, I think is the name of it. It does have your power cord and so forth and so on. It does have a Cat, I think a Cat 5 that gets connected up. This is your theory of operation. Here's your purpose. Now I'd like to say pictures are worth 1,000 words, and you can see down in figure 2-1, multiplexer operation gives you an overview of how the system works. Going from the users to the NSM to the satellite up to the bird, back down to another satellite to the NSM, and then back out to the users. It's probably the best one I've seen. This one's just explaining to you that anytime you see the word MUX, it means multiplexer. And if you see the word demultiplex, it means, or demux, it means it's demultiplexing. Again, the picture's worth 1,000 words. I cannot emphasize this enough. This is figure 2-2 port router, and you can see the number of ports and what signal format they are. Pretty wild. The reason why I highlighted this one is it's probably one of the better ones as far as non-nodal and nodal is concerned. You got point-to-point, hub-spoke, mesh, and hybrid. So it just gives you an idea. Hey, pretty cool. Gee whiz information there. Now this part where it says user port interfaces 2.3.3, it gives you the information on how many ports there are. It doesn't give you rates yet, but it does explain it as far as signal format and what it's going to be using. So highly suggest that you go through this tech order, especially chapter 1 and chapter 2. This is giving us the order wire. Now let me try to explain a little bit about the order wire. Order wire is what I call the maintenance channel. It is not part of the aggregate system. Aggregate being what the multiplexer is churning out and going to the modem to send through the SATCOM. The order wire is us. We have our own separate channel to be able to communicate to the distant to figure out, hey, we've got a problem here, and you got to figure out where that problem lies. That's our way of being able to communicate back and forth. Let's see here. Yeah. Now this is the back of the NSM. You can't see this part because the case covers it up. The connectors that you saw on the back of it when they had the little colored rectangles around it, that's the back of the case. But this sends it to the back of the case. This part right here is the front of the case that you guys will be going through. Has the power on and off, the fan, and then it has 2, 3, 4, 5, and number 7. These things are your indicators. Please pay attention to those. When you finally get everything programmed, and if you have number 5 still illuminating, you got problems. It should illuminate green, not red. If it's red, you got some more program to do, or you didn't apply the program to the NSM. You'll be able to figure it out when you get in there. All the lights are located on the front panel, not the rear. This part right here, it says G, golf. To double click on the NSM icon, this is when you're using the computer. And you need to open up the programming portion because you're going to program the NSM to do what you need it to do. You're going to activate ports. You're going to unactivate a bunch of ports. You're going to tell it what signal format and so forth and so on in what we were covering today. This gives you an idea of the tabs that you're going to be looking at, and pretty much everything is gee whiz information after that. So there you have it. Please go through the NSM 50 tech manual. It is on the test, but you will have access to the tech manual. Any questions on that one?
No, sir.
Okay. Now, this is the fun part. I screwed up and didn't print the first page. Here it is. All right. Day 2, you start lab at 12 o'clock. Correct?
Say it again, sir.
Tomorrow you start your lab at 12 o'clock. I'm looking at this correct.
Yes, sir.
Okay. Group 1 from 12 o'clock until 2 o'clock, and Group 2 from 2 o'clock until 4 o'clock. And then day 3, it's pretty much all day. So here's what we're going to be doing tomorrow. At 9 o'clock, we will be going over homework. Please make sure you do it, because every now and then I'll call what's called the law of surprise from, it's a term used in The Witcher. And I've unfortunately had the displeasure of having to write letters of counseling for people who didn't do their homework. It's okay to skip one, you know, but then again, I question, why didn't you ask me? Because I'm on Discord all the time. I'm more concerned of you doing your work. So figure out, I've had people take pictures. Airman right here sent the whole kit and caboodle of your schedule, your lab schedule. So, you know, use your phone. You can put it on Discord or whatever, or you can write it out in Notepad and send it to me. If you have Word, you can do that too. I have Word. There's not a whole lot of things I haven't seen. So if you wrote everything down, please make sure you write it legibly. So if I ask for it, you can send it to me and I'm not having to go, what the heck were you talking about on this one? I didn't understand your writing. So if you could, please write legibly. That's all I ask. You know, when I ask for homework, I'm looking for you guys to make sure that you accomplished it. Please. Any questions? No questions?